In this video, we will start looking how we can use the residue theorem to evaluate definite integrals of real variables in real-valued functions, and we'll do this using the technique of closure. This is our overview slide, which we'll spend about 5 minutes going over before we go over these topics in more detail and with more examples. We'll start with an introduction. The residue theorem can be used to evaluate certain types of real, definite integrals which appear frequently in physics and engineering. The method involves converting a real integral into a complex contour integral and then closing the contour. The residue theorem can then be used to evaluate the contour integral and subsequently the original definite integral. The closure technique is the technique of adding a section of contour to form a closed contour. So let's say we have x is a pure real variable and an integral with this form where we're integrating from negative infinity to infinity dx w of x. So we have some function of x. We're going from the real line, negative infinity to infinity, and we're integrating this function of x. And even though this integral involves quantities that are purely real, x is on the real axis, we can evaluate the integral by representing x with the complex variable z. Remember, z is equal to x, a real portion, plus I, y, and y is what gets multiplied by I and becomes the imaginary portion. So just imagine we have a z where y is equal to 0, and we have our x here. And we perform the integration along the real axis, so our path is along the real axis. And so our integral then becomes integral over r dz of wz, where z denotes a complex number. And suppose then we have this integral over a semicircular path, and this sign that looks kind of like it looks like an intersection sign from set theory. I actually haven't seen this sign in complex analysis, but here it is. It's our semicircle. So suppose we have an integral here over a semicircle that's equal to 0. So this sign here is the semicircular path of infinite radius in the upper half of the complex plane. So it's this circle here that I've drawn, and r equals infinity. So if the integral along the semicircle is 0, so this can't be guaranteed, but we'll look at what's required for this integral along the semicircle to equal 0, then our original integral over r of w of z is equal to our original integral plus the integral over the semicircle, since this is 0. But now, if we look at this, the path along the real line along with the circle, we now have a closed path. And according to our Cauchy integration or Cauchy residue theorem, this will be equal to 2 pi I times the sum of the residues of wz inside C. Our second topic is conditions for closure on a semicircular path. Remember, this closure technique depends on the integral along the semicircle equaling 0. So what we want to know is what conditions is the path on the semicircle equal to 0. And we have the answer here. So W max, and W max is the maximum value of W on the path, must shrink to 0 faster than 1 over R. So this is our condition, which we will derive. I'm not sure if that will be emphasized in your class or not, but it was in your book, so we're going to do it too. And finally, we will go over this example here, which is a real integral, but we're going to convert it to a complex number. We're going to use the fact that we're going to make it over a closed path so that we can use the residue theorem. That covers our overview, so we'll come back over here and take a closer look with the closure technique. We are going to start with x being a pure real variable, no imaginary portion, and we're going to consider an integral with respect to x of a function w of x, w also a real valued function, so to the real variable x, it's going to assign a real value, and the integral is from negative infinity to infinity. Even though this integral involves quantities that are real, it can be evaluated with x represented by a complex variable z. In particular, z is the complex number x plus iy, where y is equal to 0. And then we perform the integration along the real axis of the complex plane. That is, our integral becomes an integral over the real axis of wz with respect to z. We have this picture in the bottom corner, just to ignore the semicircle on top, and we're integrating over here on the real number line. This complex function wz now becomes valid for values of z, not just the ones that are purely imaginary or on the real axis. And we do this with the process called analytic continuation, where when we're on the real axis, we have the same function as the original real function, w of x. And we're analytic in as much of the complex plane as possible. In general, the continuation of a real function can be performed by simply replacing all the x's in a function with complex z's. So for example, w of x is equal to x squared would become wz equals z squared. Because the real axis is not a closed path, the residue theorem cannot be used to perform the complex integration. However, suppose we have an additional path, which we denote with this kind of upside down U sign or intersection sign. I'm sorry, but we did not use this symbol when I was taking complex, so I don't know if it has a name. But I think it's supposed to suggest a semicircular path. So we have a semicircular path of infinite radius in the upper half of the complex plane, and I have that drawn here. Here is our real axis, and here is our new path, the semicircular path, drawn in with the positive orientation, that is the counterclockwise direction, in direction of increasing radians, and our radius approaches infinity. Our goal is when we add the semicircle in addition to the integral along the real axis, we get this closed path, but we don't change the value when we add this section on to our real number line. We don't change the value of our original integral over here on top. That is, if the integral along the semicircle is 0, then the integral along the real line is equal to the integral along the real line plus the integral along the semicircle. And now we can use the residue theorem because we have a closed path. And we say the integral from negative infinity to infinity of wx, this is a real integral, is equal to the closed curve of wz, this is the complex, which will be equal to 2 pi I times the residue of wz inside of c in the upper half of the complex plane. I have my one-sentence summary here of what we just discussed. If the integral along the semicircular path is 0, then our integral along the real axis of wx is equal to integral along the closed curve of wz, which will equal to 2 pi I times the residues of wz, remember, inside c. And inside c will cover the upper half of the complex plane. Now we need to look at this statement here where we said if the integral along the semicircle is 0. When does that happen? So that's our next topic, conditions for closure on a semicircular path. We will start by letting r be the radius of the semicircle and taking the limit as r approaches infinity, and it's in the upper complex plane. Z then becomes r e to the I theta, where theta goes between 0 and pi. Over here we have theta equals 0. We come over here to theta is pi over 2, to theta is equal to pi. Because we're in the upper half of the complex plane, theta only goes to pi. I've just rewritten that here. Then I also calculated dz. The derivative of r e to the I theta, the r, the constant stays. We need to bring down the I. That's in front. So we have I r e to the I theta d theta. Now we can write our integral over the semicircle dz wz is equal to the limit as r approaches infinity. Theta goes between 0 and pi. And now we need dz, which is I r e to the I theta times d theta. I'm just going to move the d theta in front Then I have my r e to the I theta, and finally wz, which is w r e to the I theta. To successfully use closure as described, wz must obey this property here, that the limit as r approaches infinity of this integral should be equal to 0. To get a nicer form of this requirement, we're going to use this inequality here, which holds for any complex integral that the absolute value of the integral of f of z is less than or equal to the integral of the absolute value of f of z. Plugging our integral then, we have the limit as r approaches infinity of the absolute value of the integral 0 to pi d theta I r e to the I theta w of r e to the I theta is less than or equal to the limit r approaches infinity. And then, what did I do different? Oh, our absolute value sign needs to move inside of the integral. So I wrote this incorrectly, so I'll need to fix that. Okay, so here I wrote the absolute value sign inside the integral. And here I've corrected my absolute value sign, so they're inside the integral. The next thing I'm going to look at is my re to the I theta and my I. So remember, when we have a complex number, r gives us the distance from the origin. That's what scales our vector, our complex number. E to the I theta is what tells us where it is on the unit circle, how many degrees or radians from the x-axis. So e to the I theta is a position on the unit circle, so its magnitude is going to be 1. Similarly, if I look at I, the representation of I is e to the pi over 2 radians from the real axis. And the magnitude, again, we're placed on the unit circle, is going to be equal to 1. That makes this, cancels this and this out of the expression, so I can update this to limit as r approaches infinity, 0 to pi, absolute value d theta. I'm left with my r, my function wr e to the I theta. This next step, I'm going to remind you, this is not an equality from here to here. There's an equality here, but over here this is not an equality because we started with this inequality. Here, there's not an equality, but it's a less than or equal to. And the way we get to this next step is we think about the integral of this function w of z times r. We're going to take the r out. It's just a constant. It'll hang around. If you consider this integral the physical interpretation or the graphical representation, we often think of this as the area under this curve, and this gives us the height, and this 0 to pi gives us the base, what is that, the length, I guess, yeah. So the length, and then we have this height. So this here, if we take the maximum value of w, r e to the I theta, that will give us the maximum height that we have over this interval. So that means this integral is less than or equal to our base, the length over here of our interval is pi, and then our maximum is w max, where w max is the largest value of the absolute value of wz on the interval 0 to pi. And if we want this limit, if we want this integral to go to 0, that means w max must shrink to 0 faster than 1 over r. I have my summaries here, including the conditions for closure, so that we can do this integral, evaluate I equals the integral from negative infinity to infinity of 1 over x squared plus 1 with respect to x, and it's understood here x is a real variable, and 1 over x squared plus 1 is a real valued function of x. I start by converting my integral into an integral of complex numbers, 1 over z squared plus 1 dz, and I'm integrating only over the real axis. So the numbers I'm plugging in are only real numbers. which is how we manage to keep the equality between these two integrals. Next, I have my integral over the semicircular region, and I have 1 over z squared plus 1 dz, and I want that to equal 0. Of course, wanting it to equal to 0 versus verifying it equals to 0 are two different things, so let's do the verification. 1 over z squared plus 1, plugging in that z is equal to r e to the I theta, I have 1 over r squared e to the I 2 theta plus 1. I can factor out my 1 over r squared, and then I multiply 1 over e to the I 2 theta plus 1 over r squared, and we can see because of this r squared term, this approaches 0 faster than 1 over r, which implies over here by our condition for closure that our integral over the semicircular region is equal to 0. And now we are free to continue using our residue theorem. So I have my integral from negative infinity to infinity, 1 over z squared plus 1 is equal to the integral over the real line plus the integral over this semicircle, which then gives us an integral over our closed path circle or semicircle. And now this integral becomes easy because of the Cauchy residue theorem. It's Cauchy who came up with it, by the way, and it means that our integral is equal to 2 pi I times the sum of the residues of 1 over z squared plus 1 inside of C. Remember, inside of C means we're in the upper complex plane. Our function wz, 1 over z squared plus 1, has two poles at z equals I and z equals minus I. So z equals I is inside C, in other words, in the upper complex plane. Z equals minus I is in the lower complex plane, so it's outside of our curve, and we won't be needing to bother with this. I am one likely to forget these sort of details, but let's look then at the residue of z equals I. That's the limit as z approaches I. Using our little shortcut we learned from our last video, we can multiply our function wz, and I factored out the z squared plus 1 to z minus I and z plus 1, multiply it times z minus I, and then take the limit as z approaches I, and our answer is 1 over 2I. So this here is our residue for z equals I. And I originally calculated the residue equals z minus I before I remembered it's not, it's outside C. Now plugging into my formula, I have that the integral of r dz1 over z squared plus 1 is equal to 2 pi I times my residue, 1 over 2I, which is simply equal to pi. To review what we have covered in this video, we use the residue theorem to evaluate integrals of real variables with real valued functions, which often appear in physics and engineering. This method involves converting a real integral into a complex contour integral, then closing the contour so we could apply the residue theorem. Our closure technique, that's the technique of adding a section of contour to form a closed contour. So we considered x a pure real variable, and an integral with the form I is the integral from negative infinity to infinity dx of w of x. So x is purely real, w is a real valued function assigning a real number to the real value x. Even though this integral involves quantities that are pure real, we can evaluate x by representing it with a complex variable z. In particular, z will be equal to x plus iy, where y is equal to 0. And then we're going to perform the integration along the real axis of the complex plane. But because we're on the real axis, we're still just plugging in real numbers into wx. That is, our original integral for negative infinity to infinity of wx, x is a real number, is equal to the integral along the real axis of wz, where z is a complex number. Our goal then is to augment this real number line integration with this semicircle on top, so then we can form this closed integral. So our semicircle, what we want is the integral over the semicircle of wz to equal to 0. And again, the semicircle is a path of infinite radius in the upper half of the complex plane. So if we can achieve this goal, where the integral along the semicircle is 0, then our integral along the real line of z will be equal to the integral along the real line of w of z plus the integral of this over the semicircle, since this part here is equal to 0. But now we have a closed path, and that closed path we can use the residue theorem, and our answer will be 2 pi I times the residue of wz inside C. We also looked at the conditions for closure. Since it's important, we want the integral along the semicircle equal to 0, and we see that happens when w max, the maximum value of the function, shrinks to 0 faster than 1 over r. And we did this example here. I is equal to negative infinity to infinity, 1 over x squared plus 1 dx. We used the closed integral. We did verify in our detailed example that the integral over the semicircle will approach 0, so then we could use this closed integral, which is equal to 2 pi I residues of 1 over z squared plus 1 inside C. We found the two poles, only one is inside C, and then we also found the residue of z equals I at that first pole is equal to 1 over 2 pi I. So our final answer, we calculated pi. So that's it for this video. Thank you for watching.